Well, hello everybody, and welcome to part two and the final part of our oscilloscope kit, the DSO68. And in this video, we're going to go through and give this thing a good test and finish up the adjustments on it and so forth, and kind of see what all this thing can do. But after I shot all the video on this, I realized that I didn't really kind of max this out for what frequency band, what bandwidth this thing is capable of. So I have this thing set to its maximum seconds per division, which is 0.5 microseconds per division. And I have believe it or not, a very clean 300 megahertz sine wave going into the oscilloscope right now. And if we go in and we adjust our level, let's see here if we can get it to line up somewhere. Right there. So if we count from 1, 2, 3, 4, 5, 6, 7, you have just under 7 divisions. It's kind of hard to count. So you can see there's your 300 megahertz sine wave. Now it is showing it. But if you notice, there's some funny looking things riding on that. And what you're seeing is actually the limitation of the sample rate of that sampling A to D converter and that sampling circuit that's in there. You're actually starting to see the limitation of that sampling circuit. So this is something that happens on digital scopes when you start getting beyond the bandwidth of the scope. So you'll start seeing this some of this noise riding on there. Believe it or not, this is a very clean signal that's on there right now. I'll move you over to a scope that's capable of 300, looking at 300 kilohertz, and I'll show you that this signal in fact is very clean that's going into the scope. As you can see, this is a digital scope also, but it has a much higher sample rate. And as you can see, this is a very pure sine wave that is actually going in there. I actually have, and I'll show you here, I actually have the probes from both scopes connected at the same time. So you can see there, they're both connected. Okay, and if we go down to here and look, this one has that noise. So realistically, can this scope see at least a sine wave at 300 kilohertz? Well, yes. But realistically, is it going to give you an accurate representation of what's really going into it? No. So let's see where we start to see a clean sine wave. So here I'm down to 100 kilohertz, and at 100 kilohertz you can see that it's looking better, but you still have a little bit of noise on there. And once again, that's just a function of this scope the way it is. Okay. So really what I'm trying to say is this kit, even though it's a good kit for a beginner, it's good for people who are just getting into electronics. It's good for people who just want to learn the concept of how an oscilloscope works, especially a modern digital oscilloscope. This is not going to be something you're going to work with RF. We can look at some basic logic signals as long as they're not too high a frequency. We can look at ripple on a power supply. We can look at audio. Certainly we can look at the output of an amplifier if we just want to look at the at the output signal, because that's all within lower frequency, so it's all good with that. But when you get up into RF, this is, even though this will go up to 300 megahertz, you can see it, it starts to distort the signal pretty bad at that frequency. So there you go. And I've already had comments on the first video of boy, how we wish the days of the Heath kits were still around. This is certainly not a Heath kit. It's not of the same quality or anything like that. But being microelectronics the way they are today, this is a good representation of the kind of things that you're going to run into out there, and it gives you a good foundation on how an oscilloscope works and how to build a kit. So I still think this is a useful product, and I think it's a lot of fun to build and a very easy thing to learn oscilloscopes because of the simplicity of all the controls. They're very well laid out. So it's still worth purchasing this and and trying it out. So I just thought you'd like that, and now I'm going to continue with part 2 of the video, and this will be it. So thank you very much. All right, I have a 1 kilohertz signal going into the probe, and as you can see, it's showing up. And you can adjust the frequency this way. That's the horizontal. You can adjust the vertical positioning up and down. So it definitely seems to be working, and I'm going to play with it a little bit now, and we're going to see just how this thing will perform. But it is working. That's good news, and I'm really happy. Now that we have the oscilloscope kit all assembled and we tested it out and it works, let's get a little bit into how it works. So if you go onto the Banggood site that's going to be in the notes section there below the video, scroll down on that page, the page that this item is listed on the Banggood site, and you'll see a link on there that you can download the manuals and schematics for this. And you can also go directly to the website of the company that makes this kit for Banggood, and there it is right there, jyetech.com, and you can go, actually when you get onto their site, it's actually a really good website. You can look up this model DSO068, and they have a whole page dedicated to this little product, and it contains the firmware updates, if there are any, the firmware updating software, the service manual, the copies of everything. Now remember, this little kit did come with an assembly page, and it did come with a little basic user manual page, but the schematic did not come with it. I had to download it. It downloads as a PDF, and then you can print it out. I printed it out on this large 11 by 17 paper, so it's a little easier for you to see here as we go through it. So you can see it's a very basic design. There's not a whole lot to this thing, and the main circuit of this oscilloscope is based around this little microcontroller, and it's the ATmega64, which is a chip, if I'm not mistaken, that you see on some of the Arduino boards. So really this is kind of like mimicking an Arduino in some ways. Now of course you have your input channel, and this is just a one channel oscilloscope, not a 2-channel. And just like our DeVry Institute scope, you have your input, which is your vertical amplifier, and it has switchable attenuation. As you can see, there's AC and DC coupling, and you notice really all that we're doing with DC coupling is we're bypassing this little capacitor here. So let's scroll in a little bit and look a little closer at what we're talking about. So if you look in here, there's a capacitor that you go through that basically decouples the DC component from your waveform. So this is what you would see in that DeVry scope that we did on a couple videos ago. And if we go into DC mode, we are bypassing that capacitor. That's really all you're doing. And then of course you have ground. So there's your input select. And you can see down here on the actual scope, there's the switch they're talking about. It comes in, and you have your volts per division select, and you can see that right there. And you can have 1 volt per division, 0.1 volt or 100 millivolts per division, and 10 millivolts per division. And that would be the switch right here that's right above our input select. Then, to give you even more range, because 3 ranges is not really enough for these, we can actually have a multiplier, which comes right after it. And you can see times 1, times 2, and times 5. So by switching this top switch, times 1, times 2, and times 5, you are taking these readings and multiplying them by this number. So for instance, if I go to times 2, that means this is going to be 20 millivolts per division. This will be 200 millivolts per division, and this will be 2 volts per division. So as you can imagine, if I set this to times 5 and this to 1 volt, this scope has a maximum vertical input of 5 volts per division. And when you count the divisions, I think there's 4 divisions in there. We'll have to look when we turn it on. If there are 4 divisions, from the center line up, that means theoretically from the center you could see up to 20 volts, 4 times 5. Or if you put your trace at the very bottom of the screen and you have a total of 8, you could see a total of 40 volts. And that's if you just directly connect your signal into the input. Now, to make it even a little bit more range, the probe that they give you comes with a switch on it as well. And you can see where it says 1x and 10x. So again, if I flip this to 10x, like that, and I go back down to here, so I put this at 1, now when I'm on 1 volt per division, it's 1 times 1 times 10. And you see how we were talking on the earlier oscilloscope videos, you really have to kind of keep track of all this. The scope is not going to tell you all this stuff. Okay, so as you can tell, there are a whole lot of different ranges of volts per division that you can select on this. So that's pretty good, and it's very simple how to select it. So I like that. The vertical on this scope is very easy to use. It's as simple as possible. So there's your whole vertical section of your scope. So that would be equal to, on a normal scope, what would be your vertical right here. So this is going to select your volts per division, but you have one knob for that. And then you're going to have your times 1 and times 10 probe select, on the menus. Or this one can automatically select it if you have the correct probe. So that's all good stuff. And then your input menu here is where you would go in and select your input coupling. So really, when you think about it, this one can be a little bit more complicated because you have to go into menus to change things on the vertical. Whereas with our simple little scope kit, you just have these 3 switches and the switch on your probe. So it's very simple to change the attenuation on the input. Now this other connector, I haven't really looked at it, but I think this is an output for a test signal, and we'll get more into that a little bit later. But this is just a single input, single channel scope. Now let's move along here. As you can see, there are some adjustments here that we're going to have to do, and I believe there is an adjustment procedure in the setup manual, and we'll get into that here in a little bit to do that. But we're just going over the function a little bit. So you have all of your signal amplification and attenuation for your vertical, and it comes in here. It goes into, this is something that's different than the DeVry scope. Instead of staying as an analog signal, it goes into an A to D, or analog to digital converter. And what they're doing is they're going to convert that analog waveform into a digital word. And this is where a digital oscilloscope differs from an analog oscilloscope. So your analog oscilloscope wouldn't have this. It would just go into your sweep circuit and it would control the sweep of that trace, just like we saw on that DeVry scope. Whereas on this one, they're actually digitizing and breaking up that waveform into little pieces and then reconstructing it digitally as a digital word. And that's where where you hear about sample rate. And remember, when we did our series on oscilloscopes, this one is 2.5 gigasamples, or 2.5 billion samples per second. That means for each second of time, so if here's your time. If there's 1 second right here, from here to here, 0 seconds, it will take 2.5 billion little measurements of that waveform. So if you have a sine wave, it will take 2.5 billion little samples, okay? And I'm really making this simple. There's more to it than this because it's your sweep time and everything affects all this, but I'm giving you an idea of how a digital scope works versus analog. And a lower cost digital scope is going to have a smaller sample rate, so it's going to take less measurements over that period of time than a higher end scope, and therefore your resolution is going to go down a little bit, and also the maximum frequency that you're going to be able to measure. At some point in time, that sample rate is going to be less than the actual waveform that you're measuring. So that's why you'll usually see a higher frequency oscilloscope have a higher sample rate. And even though you might be able to look at a higher frequency signal on a lower sample rate scope, the resolution of that signal is going to be greatly degraded. And that's what this thing's doing. It can only sample at the rate at which your microcontroller is taking the sample from that A to D converter. So this is taking it and converting it to a digital word every so often, which is the clock pulses here. This is a 20 megahertz clock, and we don't really know how fast it's sampling this because I'm not a digital guy. I'll be the first to admit I can do this, but not as well as some of you. But this is going to sample that and then store it and then display it on the LCD. Now, some of these other things along here, you have a little LCD driver, as you can see, and that's the whole purpose of this chip, is to output the matrix to the little pixels on the LCD to make the image. And this section down here is your rotary controller and your keypads. So this is your button control here. That's what this little chip down here is doing. And that's going to send out the data to the microcontroller to tell it to select a certain function. So it's a pretty simple circuit. You have your vertical, you have your A to D, you have your user interface selection, your LCD output section, and then the microcontroller is really doing the whole job of the scope. That's pretty much how this is working. At the bottom, the rest of this is just power supply things. So this has different options for power supplies when you order it. Now, the one that we ordered from Banggood has a USB power. So we're using the actual USB connector. So there's the USB mini connector right there. And you can see that it comes into this voltage converter and regulator circuit. And then that provides power to the rest of the scope. Whereas at the bottom here, there's also which is not connected, believe it or not, there's this little barrel connector that if you have that option, you can plug one of these in and use a power supply that way. But in order to do that, and it says right in the instructions, let's see if I can find that. If you want to use, let's see here, somewhere it says, I'll have to look at it. Oh, here we go. Down here, when it talks about the power supply options, you can see where it says if you want to use that external 5-volt jack, you have to install this BOB2, this standoff board number 2, and jumper number 1. If you have this BOB2, yes, you have to open JP1 and you have to install D5. So if you remember on the board down here, there was a little section where we did not receive this diode with the kit. And it says even in there, D5 is not provided. So you would have to put your own 1N4007 diode in there and open that jumper if you have Bob 2, or close the jumper if you don't have Bob 2. Bob 2 is the, I believe, is the power on-off board. Let's see here. Or it's the charger board, maybe. Let's see here. Bob 2. Yeah, that's the charger board, I believe. So what you're going to do there is you could install that diode and make the jumper, and then you can power it from there. The third option is if you're using the battery, okay, an internal or external battery, and then you use the battery charger board and all these other things, and you make another jumper. And so you can see this is a very versatile power supply the way they have this, and that's why there's so much on here, is that all of this has to do with whether you're going to use USB power, battery power, or the external barrel connector. Now this one's coming back around full circle. This one is configured to be powered from the little USB port. It's a mini USB port. And it comes with that cable, which we already saw right here. Okay, so that's it. So that's what this is here, is the power supply. You have a step-up converter to get the voltage up to where it needs to be. And everything is running on 5 volts, but there is also a plus and minus 5 volts. So if you have the battery, you're going to have this little battery charger, which is going to be your charging chip and protection circuit and so forth for your lithium-ion battery. And down here, this is the UART converter, and what this is doing is this is converting your USB signal into serial data. And the only reason that this is ever going to come into play is if you're going to use the firmware updating program and you want to flash a new ROM into this unit, to flash a new firmware, that this is the thing that converts the USB signal from your computer into the old style serial signal, which is what this chip needs to program it. So this is just a built-in USB to serial port adapter. That's all that is. And again, you don't even need this unless you're going to program the oscilloscope with a new firmware. Last of all, here is your negative power supply. And again, since this circuit requires positive and negative 5 volts, all this thing does is take and create the negative 5 volts that you need for the complete power supply, for the split power supply. So as you can see, big page, but not very complicated circuit, very easy to troubleshoot. So it's actually a pretty nice little circuit. Now, again, It comes with a user manual, and it very clearly explains what everything is and how it works. And I'm going to leave this up to you guys to read it, because this comes with the kit when you buy it. So I'm not going to sit here and read it with you. We're just going to go into using the oscilloscope and see what it can do and put it to the test. Now, you can power this up through this cable from a USB port on your computer. What I'm going to do is I'm going to use one of these little rechargeable batteries, and this is, these are one of those little power banks, USB power banks, that's a battery inside a case. You charge it off your USB charger, and then you can use it to charge your cell phone, or use it as a power source. So that's what we're going to use. I'm going to plug this in and turn it on, and then I'm going to plug this in here. We're going to open the kickstand, and we're going to boot it on up. So to turn it on, all you do is push this button in, and you can see it's going to boot up. And it's ready to go that fast. Now, as you can see, as you switch this little switch to change your volts per division, it tells you. And when we go, so right now I'm set at ×1, and I'm set at 10 millivolts. So 10 millivolts times 1 is 10 millivolts per division. However, here's where you have to watch, and this is with any oscilloscope that doesn't have automatic probe sensing. I'm set at ×10. Because my probe is set to ×10, I have to mentally remember that whatever I read here, I have to times it by 10. So really, I'm at 100 millivolts per division. Now, so we don't confuse everybody, I'm going to switch it back to ×1 so that we can look at this. As you can see, we have our little graticules here. And as I said, there's 1, 2, there's actually only 3 graticules. I said 4. So we can look right now at a maximum of 10, 20, 30 millivolts positive going, and 10, 20, 30 millivolts negative going. So the first thing we want to see is we want to see how accurate that actually is. So let's take a voltage source and connect it up and just see how accurate this thing is at measuring a DC level. I have the scope set at 1 volt per division, and right now the trace is in the middle of the screen, and I have my DMM Check Plus in here. And if you remember from my from my meter video on the I forget what that was, that little meter that we did, this outputs a 5 volt DC signal. So what we want to do is, obviously right now, if I put 5 volts in here, I'm going to be off my scale, because if each square, each division represents 1 volt, then this can only read from here, it will only read 1, 2, 3. But what we can do is we know that we're looking at a positive going signal only because it's DC. So we can actually move the position of our trace, and in order to do that, we're going to hit vertical position, V pause. That stands for vertical position. We're going to push that, and you can see that function gets highlighted, and I'm going to use my knob to move it down to the bottom of the screen like this. You can see it's just right there floating at the bottom. And you can kind of see, you might or might not, but we're lined up at the bottom. If I take my scope now, my probe, and I connect it, and I haven't done this yet, so we're going to see together what happens. I should read about 5 volts. And if you look, it's reading a little bit high. And this is kind of what I was thinking. Again, we haven't calibrated this, and I think there is a calibration adjustment for this. And I think that's part of what we need to look at. But you can see it's reading a little bit high. What it should be reading right now, if we look in there, is we should be reading 1, 2, 3, 4, 5 volts. And we're actually reading more like about 5.2 volts or so. So it's not super duper accurate, but it does read. So let's take this back off again. And let's make sure that that's what voltage this thing is putting out, because you never know. So we'll take this here and kind of bring it into the shot. And if we measure right here, and you can see it is 5 volts, 4.9998. So we should see 5 volts at that test point, and as you can tell, we're not quite getting there. It's a little bit, reading a little bit high. All right, but it's close. So this is not going, you're not going to use this in place of your voltmeter. And this is something you're going to find that a lower cost oscilloscope is not going to be that accurate. Now again, we may be able to adjust some things inside here to make it more accurate, but you know, it is what it is. So let's move on now. We're now going to try to test AC with our scope, and I'm not going to switch to AC yet. I'm going to leave this at DC because, again, we can still read AC even though the scope is set to DC. We'll get more into that a little bit later. So if I just connect this as it is, you can see I just get a big mess. Now why is that? Well, first of all, the output of this is 5 volts RMS. And the RMS voltage of a sine wave will have a higher peak voltage. So the peak, the actual maximum swing of that sine wave, is going to be 1.414 times the RMS value, which means you're actually going to see 7.07 volts positive and 7.07 volts negative peak, if that makes sense, which is why it's filling the screen. Also, from the center point, it's going positive and negative. So once again, we want our vertical to be in the middle. And you can see we're still out. We're still going off scale, because now we can only read 1, 2, 3 volts positive and 3 volts negative. So we really need to go up to 0.5. Even if we go to 0.2, it'll shrink it down a little bit, but it's still going to be a little bit low. But we're just barely fitting in there. Now the other thing is this waveform is not going, you know, it's too hard to see, and the reason is we have to change our seconds per division. Remember, we have to adjust our sweep so that we can fit the signal into the screen. So we go to seconds per division, and you can see we're at 0.2 milliseconds per division, or 200.2 milliseconds. So let's open this up a little bit, and if you look, we're at 20 microseconds per division. And if we measure our positive and negative, we're going 2, 4, okay, so it's 5 volts. I'm sorry, it's not, since this is a square wave, it's not 1.414. That would be in a sine wave. So this is actually going positive 5 volts and negative 5 volts. So that's a mistake on my part. I forgot the output of these is a square wave. You can see on our square wave we have a little curvature at the beginning. It's not square. On the downswing, it's nice and square, but on the rising slope, it's a little bit curved. And the reason for that is because the probe needs calibrated. And we looked at that on one of the other videos, and you can see right here is that little adjustment capacitor, and we're going to adjust that and see if we can get it to look square. Okay, I have a little non-metallic adjuster, and I'm going to adjust this to see. It's not really making much difference, is it? So what that might be is that this may be something internal to the scope itself that needs adjusted. And once again, there is a calibration procedure for that. Adjust the compensation capacitors. So let's do that. Let's take this apart and let's adjust this and see if we can get this all to read properly. Alright, we've removed the back of the scope, and what it says here in the instructions is that the compensation capacitors can be adjusted using the built-in signal generator. And this thing actually has a really nice built-in signal generator, and that's what that other, like I said, it's an output, but it's an adjustable signal generator. I did not know that until just I started reading a little more. So very surprising. The more I'm using this, the more I'm really kind of liking it. So let's put this thing on. And it tells you to connect the signal generator output to the oscilloscope probe input. So all we're going to do is we're going to take one of these little jumper cables, and we're going to go from the input to the output, just like that. So we're just jumpering those together. Now you can do this also internally, but with jumpers, but it's just easier to do it this way if you have the BNC. Sorry, losing my voice. It's that time of year again. So we're going to turn this on. And it says to make sure that your input signal is set to DC, which it is. And it says to power up and set the test signal to 10 kilohertz. Now, what is that? How do we do that? If you push the multifunction button, you get this menu. And we're going to get into what these other things are here in a little bit. But if you scroll all the way down here, we come down to where it says test signal. If I push that, this is where it lets you change the frequency. So if we turn or adjust, they want you to turn it up to 10 kilohertz. And you can see it'll go all the way up to a 100 kilohertz test signal. So we're going to go to 10, like it says. It wants a 10 kilohertz, so 10,000 hertz. And let's see if they're saying, and they want the amplitude to be 5 volts. So as you can see, we have 5 volts set for our amplitude. So let's get out of there, and we will exit, and you can see there's a little signal on there. Sorry, I keep losing my voice here. Now, they want the time base set to 20 microseconds, which is what we have from our other 10 kilohertz test signal. And as you can see, even without the oscilloscope probe, we have that rounded waveform there. And what I'm going to just do here is I'm going to move this down just a little bit so we can get it more in the middle of the screen. And we're going to adjust our trigger a little bit where it says trigger level, and we're going to get it to lock in. You see how that little marker on the side, the little marker is actually showing you where your trigger level is set, what point you want it to trigger at. And you can see how that locked it right in when we set our trigger. As you can remember, on the DeVry oscilloscope, we didn't have that trigger adjustment because it didn't have a trigger circuit. This one does. Now, we want set switch and switch 3 to 1 volt and times 2 respectively. So we're at 1 volt and times 2. So that's all set. Adjust the trigger level to make the display stable if necessary. Change C8 to obtain the waveform as the middle of photos left. So as you can see, it starts out up here. As you can see, it starts out as a curvy waveform, and they want you to adjust C8 until it's nice and square. So the trick is to hold this thing to get lined up with the with C8, which is, let me find it. C8 is right here, so this is the one we're going to adjust. And we're going to turn it around here, and let's see if we can do this on camera. And you can see, you just turn that till it's nice and square. And there you go. Alright, let's look at the next thing. It says to keep the signal frequencies unchanged and set the amplitude to 1 volt. So we're going to go back to our menu. We're going to scroll down to test signal. And it says to change the voltage, you want to hit the level switch. So we're going to hit level. And we're going to scroll till it says 1 volt. Okay. Now, it says set switch 2 and switch 3 to 0.1 volt and times 5. So we're going to go to 0.1 volt and times 5. And you can see there, again, it is really grossly off. And it says make the display stable and then change C5 to obtain the waveform as the middle of photos left. Now here's the strange thing, what they're showing. I'm going to zoom you in so you can really see this. On the first adjustment, let me see here. On the first adjustment, come on, focus. They want you to actually have a square wave. But if you look really carefully on this one, come on. Oh, I hate when cameras don't focus. Come on, you idiot. There. They want it to actually have a little bit of a little overshoot and a little bit of overshoot down here. I'm not sure why they want that, but that's what it says to do, so we're going to listen to that. So once again, we're going to get on C5, which they're showing that right there. And that's right here is C5. And we're going to get on that. And then once again, around the camera, holding everything precariously, let's try to adjust it. And there you go. Once again, I just put that little tiny overshoot like they're saying. Now, again, I'm not sure why they want that little bit of an overshoot, but we're going to do that. Now, if that comes to bite us later because that's like a misrepresentation, we'll go back and fix it. But we're going to follow the instructions because they probably have a reason for it. Okay. Remove connection between test signal output and scope input. Adjustment is done. So they're saying that that's completely finished. I've now connected the scope back up to the test point, to our DMM Check Plus. I set the DMM Check to have a 10 kilohertz output at 5 volts peak to peak square wave. And as you can see, it's reading incorrectly. And I have the probe set on times 10 because this capacitor works on times 10. So what we want to do is we want to adjust this for accuracy and we want to adjust it for flatness. So we're just going to take this little adjuster here and we're going to turn it until everything flattens out. And you can see we now have a really nice, we did have, there. We have a bad probe, guys. You can see that capacitor is not working real good. There. Nope. Alright guys, we got a bad, looks like we got a bad, I'm using a ceramic adjuster. And what looks like is this compensation capacitor in here is faulty. And because of that, it's not working right. So guys, there's a thumbs down right there. We got a bad probe with our kit. So let's get another probe and put on there and compare. Alright, I just grabbed another probe and you can see there it is. And unlike the other one, instead of being on the connector having the capacitance comp adjustment, it's actually on the probe itself on this one. So we have everything else set the same, and you can see we still have our waveform. And let's see if I can get this whole thing into the shot. There we go. And I'm going to just go ahead and adjust this. Right there. You can see we have a nice square waveform now. And now I'm going to expand it a little bit and see if we can get it even a little bit closer. And that's about all we're going to get. And you can see there it is. Now if we really wanted to get this perfect, rather than using our the built-in test signal, and I think this is actually there, you notice we have that little tip on there. That's from that adjustment manual. If you notice, I'm at 0.1 per division and times 2, and they wanted 0.1 and times 5. If I go to times 2, I'm thinking our little adjustment is incorrect. So we want to change that and flatten it out. So I'm going to take the back off and I'm going to adjust C5 and C8 again to make sure that they're correct using the probe itself for the signal, because you're actually putting that in the circuit. So it would be better than just our jumper that we used. So let's do that. Okay, so we've adjusted through the probe this time instead of just jumpering the test point in there, because that probe actually kind of factors into it. It is a little bit silly how this thing adjusts compared to other oscilloscopes, but it works. It works. It's like I said, this is a $60 thing. It's not a $2,500 scope, but it's working pretty good. So now that we have that, let's get out a signal generator and let's look at some of the different things that we can look at on this. The first thing we're going to look at is our DC once again, and looks like I just rebooted the machine. So let's connect this up, and I'm set to 2 volts per division. And if I connect this up now, you can see I'm pretty close to 2.5 divisions, which would be 5 volts. If I go down to 1 volt per division, or 5 volts per division, you can see it's right on the line there of 1 graticule, which equals 5 volts from our 0 point. If I disconnect it. Now the one thing I will tell you is the way this kit fits together, these switches are finicky and you have to make sure you positively click them into position. You can get it clicked halfway between 2 clicks and it will short both of these poles together at the same time and mess up your scaling. So if you have a problem with this being accurate, make sure that that the switch is positively switched in. All right, now let's look at some waveforms. All right, so we're going to start out kind of simple here. And we're just starting with a simple 1 kilohertz sine wave at 5 volts. So the first thing I've done is I just connected it up here. You can see just with the probe. So we're using the probe. Probe is set to ×1. And when I go in here, you can see my time is set to 0.2 milliseconds per division. And my volts is set to 2 volts per division. So there you go. So we have, if I count the gradicules, this should be able to tell me if my time base is accurate or not, because frequency, as you remember, is 1/T. Oh, and by the way, we're using the Field Tech here that we did the little video on. Since we're not connected to anything that's connected to the line, I'm not really worried about it. This will work just fine, and it does output a good, solid little signal. So frequency is 1/time. So if I have 1 kilohertz or 1,000 hertz, 1,000 cycles per second, if I take 1 divided by 1,000, because it's 1/T is frequency, you can see 1 complete cycle should take 1 millisecond, or 1/1000th of a second. So if I look on my gradicules here, and I want to count from the first time it crosses the 0 till the next time the positive crosses the 0, this is 1 complete cycle, because you can see it goes to its peak, goes through the 0 volts, goes to its negative peak, returns back to 0 volts. So this should be 1 millisecond long. If I'm looking at 0.2 milliseconds per division, then that should be a total of 5 divisions, if this is correct. So if I count 1, 2, 3, 4, 5, and you can see I've lined up, I've used my trigger level to adjust it right at the beginning, and you can see it perfectly crosses over at 5 divisions. 5 times 0.2 milliseconds would be 1 millisecond. So why did I say all this, and why are we looking at all this? Well, what that's telling us is this is accurately displaying a 1 kilohertz signal, and the scaling, our divisions, are actually accurate. Now, once again, we're looking at 5 volts sine wave. So again, if we do our volts per division, I'm going to go 1 volt per division, and if I take my vertical position and I line it up directly on a bottom line, in a perfect world, what we should see is 1, 2, 3, 4, 5 volts. And you can see it's reading a little bit high. So once again, this scope isn't extremely accurate at measuring voltage, but maybe the scope is outputting, or maybe the signal generator is not outputting the signal accurately either. So let's take our known good oscilloscope and connect it up, and let's see what we get. I now have the Tektronix oscilloscope connected, and you can see that the waveform is very similar. Now, look at all this noise on here that's going on. If you look at it, there's all kind of ghosting, there's all kind of noise, and we don't see that on our other scope. If you look down here, it's a nice clean waveform. The only thing is that the voltage is a little bit off, or at least we think. That's why we're using this other scope. But if you look up here, would you say that this scope here is not as good because it's not locking in and it's noisy? Well, no, that's actually not what's happening. It's that this scope is a little bit too good. Let's look at why. If I hit the menu, right now we're looking at the full bandwidth. This is a 300 megahertz scope, and it can even pick up the little minute noise that's sitting in the background. If I change the bandwidth and turn this into a 20 megahertz scope, look how locked in and accurate that gets. So that's really all that you were seeing there. Now once again, if I move my trace to the zero crossing and I measure, once again I'm at 200 microseconds or 0.2 milliseconds per division. 1, 2, 3, 4, 5. So there's 1 millisecond from here to here. And that shows that that is in fact a 1 kilohertz signal. And you can see up here our frequency meter is bouncing right around at 1 kilohertz. Now the RMS voltage is 1.73 volts, and if we take 1.73 times 1.414, you can see that that's giving us about 2.446 volts peak. Times that by 2 for peak to peak, and you can see we're getting about 4.89 or 4.9 volts. So it's a little bit lower than our actual 5 volts. It's really close, and this one is showing it to be a little bit higher. Okay, so again, this is not meant to be a voltmeter. This is meant to be an oscilloscope to look at waveforms. And remember, it's a student model. It's a little kit that we built. It's not going to be perfect. Now, I believe if we had access to the source code for the firmware, we could actually write something in there to be able to adjust that accuracy. And there may even be something for that. I just don't know enough about this kit yet to know that, so that we could bring it in. So you can see it's working pretty well. Now, what else can we do? If I hit the adjust button, let me turn the lights back on. That other scope's hard to see in the dark, with the lights on like that. If I turn this back on, if I go down to frequency meter and hit enter, it becomes a frequency counter. And you can see it's a little bit slow refresh rate, but it's very accurate. It does a really good job. Let's see here. And you can see if I change my frequency, now I'm up to 2 kilohertz. Let's see what we can do. There's 100 kilohertz. Let's see how far it can go. 200 kilohertz. 500 kilohertz. 600 kilohertz. Ha! There's a 1 megahertz signal. There's a 10 megahertz signal. And you can see it starts to drop off after 10 megahertz. Let's see how far it can go. There's 5 megahertz. Can't read that. So it probably, there's 2 megahertz. 1 megahertz. So this thing can count up to about 1 megahertz. So it's got a 1 megahertz frequency counter in it, which I think is pretty darn good. It also does fast Fourier transform, so you can look for distortion on a signal. Now, that would be really good to use like if you hook this little thing up to your amplifier and you want to check for distortion on the output of your amp. We could use this function for that. You can save a waveform. You can recall a waveform from memory. You can send the screen to, if you have a USB interface with this, apparently it'll let you send the screen to the application. You could send the waveform data. You can change the record length time when you're recording. Change your trigger position. You can you have a test signal generator. So this has a little signal generator built into it, which I think is great. And again, it's not, it doesn't give you a whole lot of adjustments, but it'll go from 1 hertz. So this thing goes all the way down to 1 hertz or 1 cycle per second. And you can see it's pretty neat how it adjusts. You have quite a range, clear up to 100 kilohertz. So that's quite a good signal generator, and it's just a square wave output, but perfect for, And then amplitude, if you hit the level button here, there you have 0.3, 1 volt, 3 volt, 5 volt, and there you go. So not super versatile, but it is a adequate little test signal generator that you can use to calibrate the machine, or use it as a actual square wave test signal, which is actually, I think, is pretty neat. And there you go. Going back to the main menu, you can see that you can restore all the default settings with that. You can reboot the scope if you need to. I don't know why you would need to do that, because you can just shut it off and back on. And then to exit the menu. So there you have it. And of course, let's see here. It's getting a lot of noise here, but anyways, as you can see, the scope works really well. I'm pretty relatively impressed with how it works. So there you go, guys. What do you think? Well, one thumbs down is I got a bad probe with this. You can't adjust it. So these probes can actually be purchased very inexpensively online. You can get these anywhere. This is a 20 megahertz, and if you type in P6020 oscilloscope probe, you'll find these are only a few dollars each, a couple dollars. But neither here nor there. I'm sure if I wrote to them, Banggood's very good at returning products that have problems with them. So I may write them and let them know about that, but it's not a big deal. I had extra probes, but for you, there you go. But they're cheap probes, that's what you get. Anyways, my evaluation of this at the end is that it was a little bit difficult for the soldering, because everything was so tiny. You needed to use a very small tip of an iron on your iron, and something like a little pointed tip like this, or a little bent pointed tip like this, is really what you want to use on this. Normally I like the chisel point tips that come with standard with a soldering iron. You don't need anything really fancy, but you definitely need a small tip. It was tricky. The instructions were pretty clear. If you read this page front to back, it's very clear how to put this thing together. Although I will say, like I said earlier in here, you probably want to put those standoff boards on before you put some of the taller components that go around it, the surrounding components. It just makes it easier to get on those little tabs and tack those edge connectors of those boards on. Very easy for a beginner with oscilloscopes. If you're new to oscilloscopes, very easy to use, very intuitive how they did this. So all your vertical adjustments is these switches on the left. Your vertical and horizontal positions have their own separate buttons, which is really easy to use. Your horizontal or seconds per division is right here. All the information is on the right hand side of the screen. The thing that the wheel is going, or that your knob is going to adjust, is highlighted, so you can see if I move around here all these different things. This will do a triggered sweep. So if I go to turn this off and I set it to single, and then I touch this on here, and you can see it holds the waveform. Alright, let me back off and show you what I'm doing so you understand what I'm doing here. So I set it to, I turn off the hold, that rearms it, and I touch, whenever it sees a signal, it triggers, and you can see it says hold again. Let's do it again. And you can see all this noise right here is the noise of me touching that little metal contact on there. And you can see now I can do whatever I want. It's actually frozen the waveform. So if you're just trying to capture a pulse or something, this is actually a true digital storage oscilloscope. The trigger works really well on it. I just can't complain any about it. Now, it's not very accurate at measuring volts, but you know, if I were going to look at you know, just looking at a waveform or something, this is good enough. So yeah, this thing gets a thumbs up. It's a very good learning tool for somebody new to this hobby. It's a usable device when you're done, as you can see. The instructions are pretty clear. If they ever come out with new firmwares, you can flash new firmwares. You can, I believe there is an interface that you can interface this to a computer if you want to capture and store waveforms and so forth. So yeah, this thing does a whole lot. I really like it. So let me know what you think down in the comments section. I hope you enjoyed this little video in our oscilloscope series. So what do you think? You know, when you look at 40 or 50 years ago or 30 years ago, they had those little vacuum tube scope kits that you built for students versus a modern you know, digital oscilloscope kit. What do you think? It's changed a little bit, hasn't it? But when we looked at the schematic, a lot of similarities and some differences. So there you have it. I have a lot more videos here to do and a lot more coming up. So and it took me a couple weeks to get through this little video because I've been so busy lately. It's just crazy. I literally barely had the time to come down and finish this up today. So apologize for taking so much time to get this out to you all. But I hope you enjoyed it nevertheless. Hope you enjoyed this video. Remember to give me a thumbs up if you liked it. And as always, I wish you all the best of health, peace, joy, and happiness in your lives. And can't wait to do the next video for you all. Have a great day, and we'll see you next time. Bye-bye.